Okay, we're going to continue on page 238 with a little reminder, which is at the top of the page. I showed you this, and it seemed satisfactory enough to most of you, at least you didn't complain about it, that if I tell you that this is two different versions of the derivative, and they are equal to each other, then we can split up those differentials this way, by cross multiplying, basically. Remember that?
Yes.
There's a proof of that. It's rather lengthy on page 239, and we can go through it if you want.
I trust
No, no, we're not doing it. Is it?
That's fine with me,
Is it?
I think we
but
got
I can show you if you like
No,
why this is the case,
I think.
rather than just, oh, these two things are different versions of a derivative, and if we cross multiply, this is what we get. But if you're satisfied with that, we can run with it. Everybody okay with that? Because you'll notice in the 10 box at the bottom of page 239 after the proof, they say the same thing. Virtually the same thing. That's the conclusion. But when it says estimating change of differentials, they actually go through it and show you what's going on. And it's a rather difficult thing to read and do. But you can, it's okay in math to go through life saying, someone proved it, someone knows it's true, and believes that it's proved properly. I'll take that. If you want to do that, we can. Want to do that?
Yes.
Okay, me too.
That's good.
All right.
That's super.
So just to get this all back in your mind and gelling properly, I'm going to do example 7 with this fact right here. Because the notation in example 7, the way they write things is slightly different. In example 7a, it says, this is what we're supposed to do. We're supposed to find d of tangent 2x. What that means is they're saying find dy, but they're putting y in there. It's not d times it. It's d of this function y. And they're putting the actual function y there. Do you understand the difference in notation?
Oh, yeah.
So that means if this is d, the function, then I need to find the derivative of the function and slap a dx on it, basically. Okay? So the derivative of the function, this is why the derivative of that function is going to be what?
Squared.
2 because of the chain rule, secant squared because the derivative of tangent is secant squared of 2x dx. Done. It's just this is weird looking.
It is weird.
This is y. They're just putting y in there. They say find the derivative of y. Or no, find the change in y. And we're going to use this fact to do it. This just looks bizarre. So in the next one, the b part, they have find d of x over x plus 1. Means this is y. This is y right here. Without saying y equals now find dy, without doing that, they just dump it all together into one expression. Oh, x plus 1. All right. That means to find the derivative of this, slap a dx on it. Okay, so what's the derivative of this? Load high first. X plus 1 times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Everybody follow that?
Yeah.
Dx, and then we should clean it up if possible. So we have a little bit extra here. That x minus that x is just leaves a 1 over x plus 1 squared. And you can put the dx up here.
Is that really just the answer?
Yeah. It's just that the notation is weird. So I wanted to show you what the notation is doing to you. Y'all understand that that translates to that and you see it happening? This is the y.
Don't be a sucker for that.
Yeah,
I'm a sucker for
it.
What'd you sucker for?
to cancel the top and the bottom.
Oh, yeah, no, don't sucker for that.
Don't sucker.
I sucker for it.
Oh, don't sucker.
Don't sucker
for
it. Everybody okay with the strange notation and how to handle it?
That was times.
Because you'll see something like that.
Yeah,
Yeah.
for those times
You okay with this? I'm not seeing it in your face. I'm just wondering. You and Rachel are doing. Right. So then they do this proof and they arrive at the same thing. The same thing we're going to keep using here. So I want to go over and now we're going to apply it to some actual problems. In example 8, it says we have the radius r of a circle that increases, the radius increases from an a of 10 to a 10.1. So just looking at that, what is DR? Top of page 240. I heard it.
0.1.
Yeah. DR is, conceptually speaking, the change in the radius. And the change in the radius from 10 to 10.1 is 0.1. Okay? Y'all understand what I'm asking when I ask you for DR? Okay. It says use DA. What does DA stand for?
The change in area.
The change in the area. Use that to estimate the increase in the circle's area A. Compare the estimate with the true change, delta A, and find the approximate error. They're going to have you find approximate errors a lot. It's not very hard. Once you've done it 1 or 2 times, it's okay. You can handle it. So we've got that circle there. They've shown us, they've got that ring around the outside, and that ring is 0.1 wide. That's your DR, as it shows you. And we want to know what the area of that blue ring is, basically, because that's the change in area as we change the radius, right? Okay. So we need an area formula. Area of circle is pi r squared. And we wish to find dA. That's the differential dA, and we're going to have a dr over here. That's what we've been doing all day. Well, and yesterday too, yeah? Okay, so what is the derivative of this? Thank you. Gosh. And then here's the dr that used to be under here, yeah? Okay, with me? Okay. So the approximate change in area, because all this stuff, this is right here, because this is linearization, and that's what the proof's all about. They use a linearization to prove this. This is actually approximate. As long as we stay close and don't make a huge change in R, we're going to get a really, still just a guess. Not a guess, an estimate. So the approximate change in the area is going to be 2 pi, what was R? 10, what was dr? 0.1. So what is the approximate change in the area? Yeah, 2 times 10 is 20, and a tenth of that is back to 2. That's the approximate change in area. In other words, when the radius is 10, if we just go another tenth out and make the radius 10.1, we get an increase of area of about 6.28 square units, approximately, according to what we've done. Do you understand the concept?
Wait. How'd you get 2 pi times 10 times 0.1? Just 2 pi.
2 pi times 10 is 25, 0.1 and 20.
It's like 10 times 1 over 10.
Oh, okay. Okay.
Suckers out.
Yeah, here's another way. A tenth of 10 is 1, so you're left with 2 pi.
Okay, yeah. That makes it.
Everybody good?
Yep.
That's the approximate change in area. What's the actual change in area? How do you find that?
Just like 10.1.
You take, listen, this is going to be used a lot, so pay attention to this. To find the actual error in this estimate, you would take the true value, subtract the estimate, and divide it by the true value, and multiply it by 100 if they want the percent change. I'm going to put that in parentheses, not because it's mathematically correct, but because we may multiply by that and we may not. It just depends if they want a percent change. So what is the true value of the change in area? How do we find that? Into the original area, you plug in 10.1. That's the actual change. I mean, that's the, okay, I lied. Wait a minute. Don't write true. Yeah? Yeah, that'll work. Yeah, yep, that's right. So what's the true area?
Area of the bigger circle minus the smaller one.
Okay. So it's going to be the area when it was 10.1 minus the area when it was 10. Do that. Leave it in terms of pi. So I guess I'll erase this over here and show you what the discussion was we just had. Brent and I just had. So it's going to be the area at 10.1 minus the area at 10. That would be the true change in area, right? Does that make sense? I'm going to leave it in terms of pi, so I'm gonna have pi times 10.1 squared. I need a decimal for that, but don't multiply it by pi, minus 100 pi, because that's what 10 squared is pi. What's 10.1 squared?
Oh, I don't know.
What's 10.1 squared? 102.01? So this is 102.01 pi minus 100 pi, which is what? 2.01 pi. That's the true change in area. Our estimate was just 2 pi, only 100th off. This is how you actually find the actual area. You take the 2.01 pi and you subtract 2 pi and you divide it by 2.01 pi.
And then times by 100 to get a percentage.
Yeah, times 100 if you want a percentage. Just give me this decimal first.
0.004975.
So practically 0.005. If we made a percentage out of that, it would be 0.5% approximately. It's a 0.5% off our estimate by using this as opposed to doing this. You might think, well, it's just about as much of one as the other. We might as well be accurate. No, you're practicing using estimates today, so do the estimates, use the calculus. But you're not off by far. 0.5%. You follow that? True minus estimate divided by true times 100 if you want a percentage. Okay, now let's try example 10. No, let's try example 9. Example 9 is very, very interesting. It comes out kind of strange. We'll discuss why in just a minute. Everybody got this? We good? We're gonna erase this?
Yeah, go ahead.
All right. So now we're gonna talk about a bicycle tire. My bread and butter sort of thing. Okay, listen up. Shh. Shh. Inflating a bicycle tire changes its radius from 12 inches to 13 inches. So the tire is an inch thick when it's inflated. Use differentials to estimate the absolute change, relative change, and percent change. What? What is all that? You see the table just above that? It talks about absolute, relative, and percent. Would you like to discuss that a little bit first? Yeah. Okay. Look at that table just above example 9. An absolute change is when you find f of a plus dx minus f of a. That's what we did to find the true value with the area. We did f of 10.1 minus f of 10 to find the absolute change. The subtraction. That make sense?
Yep.
Okay. When you want to estimate the absolute change, you use this thing we have on the board here, which is f prime of a times dx, the change in x. Okay, if you want to estimate the absolute change. Are you with me there?
Mhm.
Relative change. They take the change in f, which we figured up above. See that? The delta f up above? Just above it?
Mhm.
Delta f divided by f of a. That's how you figure a relative change. If you want to estimate it, you take the differential of f, like dA, and divide it by the function evaluated at a. That's how you find a relative change. You may want to come back to this when they ask you to find those things. Percent change, you take the relative change, multiply by 100. Whether you're estimating it or the true value. So percent change, you just got to figure the relative change, multiply by 100. That's what we did with the true minus estimate over true. Okay, or not?
Yeah, we're good.
Okay. Example 9 wants us to find all of them. So, it says to find the absolute change, the relative change, and the percent change in the perimeter of the tire. Absolute change. How are we going to do that? First of all, what's the perimeter of the tire? What's the formula for perimeter?
That's just circumference to pi r.
Yep, 2 pi r. Okay, so now let's plug some values in there. We're trying to find the absolute change. That is delta p. The change in p. How are we gonna find that?
The absolute change?
Yes,
So.
Plug in 13,
so 2 pi times
13.
13 minus
2
pi
pi
times
times 12.
minus 2 pi times 12. What's that?
Oh, yeah.
2 pi.
2 pi.
This is 26 pi minus 24 pi.
Yeah. Yeah.
Okay? And 2 pi is about 6.28, because this problem has context to it. We're going to use decimals so we got some idea about how much that is. 6.28 what? Inches, about. This is approximate. So in other words, if you measured the tire before you inflated it with a tape measure like you use in sewing, and then inflated it and measured it, you would get 6.28 more when you measured it when it was inflated. Measured it around. That's what we got there, okay? The relative change would be what? Notice how they do the relative change up there. They take the delta F, which we just found to be 2 pi,
Over,
and divide it by what it was before we inflated it. The original, before we made the change. That's F of A.
Yeah.
So it would be 2 pi divided by 24 pi. So the relative change is 2 pi divided by 24 pi. Now, how many of you are completely lost at this point?
I'm not lost, I just don't see how that relates to the problem. Like, what, it's not even close to like this.
It's the change divided by what it was gives you some way of figuring percent change. Now, I'll come back to just a minute and it'll make more sense to you maybe. If you've got something on sale and it went from $10 to $7.50, and you don't want to know the percent drop, you would take the difference in those two, which is 2 pi. Difference in the two things we're dealing with, which would be 10 minus 750 would be 250. That's the difference. And divide it by what it was, which is 10. You see what I'm saying? Okay. So we take the change in the circumference and divide it by what it was before we made that change. Okay? So that thing that I wrote down for you right here, where I said true minus estimate over true, maybe this would be better for you. You take the new value minus the old value before you made the change and divide it by the old one. This is your delta P. It's a change in P, right? That's how much it changed. Divide it by the old one to tell you the percent or the relative change in it. That's what's going on here. Take the change in, which I figured out up here. I take the change in it, which is new minus old, and divide it by what it was before I made the change. That's how you find relative change, okay? Y'all following me? All right. So that's going to be what? 1/12, which is 0.0625?
Sure.
What's 1/12? 0.08.
And then 3 repeated.
3 repeated. Okay. So that's approximately an 8.3% difference change.
That's a big difference.
And that's your percent change. Yeah, that one's big in this one. Well, think about it. You got a flat tire and you got a full tire. It's a pretty big change. Okay, so the approximate percent change is 8%. 8.3 is good, whatever. Do you think you can handle the absolute, relative, and percent?
Yeah.
Pretty good. Okay, we're going to switch gears here a little bit and use all the things that we've learned about so far to do three more examples. This will take your concentration. Oh, I shouldn't have erased that. So if I have y equals, no. I'm going to write up here that dy is equal to f prime of x dx, and that's an approximate. Okay, that's what we're using. What did we also say for relative change? What's the symbolism for relative change?
Delta F over F of A. Yep.
So in other words, you said that the relative change in things was,
Delta F.
yeah, the way they wrote it, delta F over F of A.
Yeah.
Can I do this? Can I write this as dy over y?
Yeah.
Do you understand that's about the same?
Yeah.
We good?
Mhm.
This is evaluated at A, yes, but we'll take care of that as we go along. But that's another way of writing. It's a little more clean and a little more calculus-y. They're the same. Are we accepting that?
Mhm.
All right, so example 10 says this. Suppose the Earth were a perfect sphere. Well, no, it's not. Bulging at the equator because it spins faster than it, right?
Right.
But we're going to assume it's a perfect sphere, so let's make that assumption. And we determined that its radius is 3,959 plus or minus a tenth of a mile. 3959. That's practically 4,000 miles, and we are going to allow an error of a tenth of a mile. That's pretty good measuring, right? But we want to know what the effect of having that much error, see it says, what effect would the tolerance of a tenth of a mile, either way, have on our estimate of Earth's surface area? So if we made a tenth of a mile mistake, how much of a mistake would that be in the total surface area that we're going to do? You see what I'm saying? It's not as significant as you think, but it's more significant than,
It'd be pretty big in the end.
yeah, okay. Here's how we tackle a problem like that, folks. We start off with a formula. What do you suppose it is in this case? Surface area, because that's what we're trying to figure out is what the error in that's going to be. So surface area of any sphere is 4 pi r squared. Okay, we're talking about a sphere here, and the radius right here is 3959 plus or minus 0.1. Not very much error in measuring the circumference. Okay, so this is what we're dealing with. If I go ahead and use this right here, this idea right here, what should I do next? I should rewrite this over here so I don't run into my sphere. Just a minute. Okay, so I'm just moving that over there so I got room to work.
Cool.
Okay, what should I do? Find the derivative. We'll call that what? ds? Isn't that the differential for surface area? Equals what? dr. Okay, so this says, and conceptually speaking, this means the change in the surface area will be equal to this formula, this derivative, times the change that we're allowing in the radius. Now, we don't have to use plus or minus. It's just going to be a 0.1 change, one way or the other. If we overestimated it, then our surface area will be overestimated. If we underestimated, then the surface area will be underestimated. So I'm not going to put the plus or minus in. dr is 0.1. R is 3959.
Right.
Okay. So, and this will be the change in the surface area because of this change in R, or it's approximate. So I have 8 pi times 3959. Do you see what I'm doing?
Yeah.
Times 0.1. Do that. Give it to me to the nearest whole mile or square mile.
9950.
9950 miles squared. What? You guys all know what a square mile is because of where we live, right? You got nearly 10,000 of those. That's how far off your estimate of the surface of the Earth is. But relatively speaking, it's not very much. It's about the area of Maryland. Got any idea how big Maryland is?
Not very.
It's pretty small. It's over there on the East Coast, and they're pretty small over there. So that means that you will either, if it is off, if the true value of the radius is off in your measurement here of this is off by 0.1 either way, you will either over or underestimate by about 10,000 square miles, which isn't that much, but that farm, it'd be a lot,
Yeah.
right? Okay, so it's a pretty good size number. It's amazing that 1/10 of a mile will cause that much of an error, but relatively speaking, with the total surface area of the earth, it's not much. How would we find the relative change? How would we find the relative change? You would take the dy, which we just found, 9950, and divide it by what it was before we made the error or before we considered the error, which would be 8 pi times 3959. Right? Would be the function before we introduced an error.
But it would be the derivative function, not the.
No, would be the derivative. 9950. This is y. This is the function y. Oh yeah, you're right. So we should have come up here and done that. Would have been 4 pi times 3950. You figure that out, and you're going to see how tiny it really is.
You have to square.
Square. Tiny, huh? Yeah. So it seems like a lot of square miles, but when you consider all the square miles on Earth, it's not much of a change. Okay. We okay to move on to the next one or not? Yes or no?
Yeah.
Number 11 is really going to throw a cork in things for you here. You have to really think with me. You might want to take a picture of it when you're done so you can see all the notation and stuff. Here's what we're going to do now. We're still considering the surface area of the Earth. It still has the same radius, plus or minus something. It's not going to be 0.1. What we want to do now is reverse the idea and ask ourselves, how accurate do we have to measure the circumference so that the error in the surface area is 1% or less? You understand the question?
Yeah.
You may not know how to find it, but you understand what we're looking for. We're looking for the tolerance that we will allow in the mistake measuring the circumference. How much will we tolerate mistake-wise if we wish to calculate the surface of the Earth to within 1% of its true value? Do you understand what we're after? Okay. So let's start out with just the concept of surface area. We want the surface area to be the change in surface area. Sorry. We want the change in surface area to be less than or equal to 0.01 of the true surface area. You understand the notation? Okay. And we wish to find the change in radius or the error in radius, which would be what? What do we call that? We're trying to find the change in radius that will accomplish this. dr. We're looking for dr. Right? Let's put some formulas in here. Do you remember from the previous problem what ds was? It's pretty easy. I'll do it again here. What is it?
8 pi r dr.
Okay. So this is 8 pi r dr. And we wish that to be less than or equal to 0.01 of 4 pi r squared. That's the surface area. How we doing? You okay?
Yeah.
And what do we want to find?
dr.
dr. dr will be, these will be positive numbers, so we don't have to worry about this. 0.01 times 4 pi r squared over 8 pi r. That make any sense? Okay. So we do a little arithmetic on this. That's going to be 0.04 pi r squared, and this will be 8 pi r. I'm going to lose the pi's. I'm going to lose an r. This one you can cancel. There's no plus or minus sign. And 0.04 divided by 8 would be
200. 0.005. Yeah, so 1.
right? Now, what is, so that we have some idea on mileage here, this is DR. In other words, if you want to change that to a percentage, we have to be less than 0.5% away from the true value of R to be less than 1% error in the surface area of the Earth. But what was the radius we were working on?
39.59.
What's 0.005 of 3959?
19.795.
We can be off by nearly 20 miles. And in the other one, we were only off by 1/10 of a mile. So that 99.50 that we have is way less than a 1% error in the surface area. Way less. Because we're allowed nearly a 20-mile error in the measurement of our circumference. And the surface area calculation will be off by less than 1% if we do that. So you see, the last one we did where we got the 99.50 seemed like a lot of square miles. Comparatively, it's insignificant, as some of you who actually calculated that found. It's just the 0.1 error is very small. Okay, so the key to this is to be able to write this. Because if you can write that, you can make substitutions all over the place. But you've got to understand what your question is. So that the error or the difference in the true surface area, the change in the true surface area is less than 1% of the, whatever that is. And then you start making substitutions. Okay? Last example, number 12.
There's a row on the other side. Oh, there's not.
What?
No, there is.
This is a 3.
Yeah, it's a cool one too. Number 12 is going to exploit this idea right here, and you're going to have to be able to recognize it when you see it. And it's kind of hard. It's kind of hard to see it. So we're going to talk about, this one's all about relative change. And it talks about doing, going in with a stent. You know what a stent is? Like open up an artery. Open it up so that that the fat and the accumulation in the artery doesn't, it opens it back up and stretches that fat and the artery so that, and it's a hard stent so that blood can flow through it better for a while. Then the plaque starts to build up on the stent and they got to go take that one out, put a new one in. And then by then you're probably dead.
Temporary fix.
Okay, listen up. In the late 1830s, this is a while ago. I didn't know they were doing stents then, but he did some work on this guy. He says, a French physiologist, Jean Poisoy. I was not having any idea how to pronounce that without that pronunciation thing on it. Jean Poisoy discovered the formula we use today to predict how much the radius of a partially clogged artery has to be expanded to restore normal flow. We use this formula. V equals KR squared, or KR to the 4th. The volume of blood flow through a certain place is equal to K times the radius of the artery to the 4th. Okay, that's how much blood flows through it. And it says that the volume of the fluid flowing through a small spot pipe or tube in a unit of time at a fixed pressure. So if you've got high blood pressure, this is supposed to reduce it some too. Fixed pressure is a constant times the 4th power of the tube's radius. Okay, so here's the deal. How will a 10% increase in R affect V? They are not giving you any other information except for this 10%. And that's the reason why we have to deal in relative things, because they give us nothing specific like the 39.59 from the last one. We don't have it. We don't have any of that. We're saying if we increase the radius by 10%, whatever that radius is, increase it by 10%, how much will that increase the blood flow? And it'll have to be as a percentage, right? So even if you have no idea how to begin this, being in this class, in this section, what do you suppose we should do? There you go. Okay. So we're going to find the change in volume. That's what that represents. And that's what we're after, right? But it'll be relative.
Is K a constant?
Yes?
Okay.
dr. Don't forget your differential. So we've got our derivative. We have a pretty good idea, conceptual idea what this is. This will be the change in blood flow per the change in radius. 10%'s got to go in there somewhere. There are no plugins except for the 10%. We want to find the relative change in the volume, right?
Yes.
Will this be the relative change in the volume?
No.
No. This will be. Can I just do that because I feel like it?
No, that's.
Gotta do both sides. by-
Not unless you do it to the other side as well. We want the relative change in volume. You following me or not? So we have to make this happen. So we found the derivative, but it wasn't really relative change. It was the change in V, but we had to divide by V here, which means our relative change in volume is going to be 4K times R cubed. We still don't know what R is. What's dr? Do we have a dr? Hang on. I'm going to leave this dr for just a minute. Maybe you'll see why we want to do that. Volume is what? Kr to the fourth.
You put pi instead of a.
Oh, thank you. It's just a habit. Thank you. Okay, can you simplify that for me? What's that?
4 dr over r.
So the K's gone. I lose 3 of these, and I have 4 over R dr. I'm going to leave it out here. No. I can do that. 4 dr. I'll do that. Do you see a relative change in what I just wrote? I do. That's the relative change in R.
No, see, I saw that, but then you started saying no. Don't see her.
This one is all about recognizing this thing in both places. This is the relative change in R. 4 times that relative change will be the relative change in volume. So if we change, the relative change is 10%. It's not really 0.1 here. It's 0.1 of R. The relative change is 10%. And that's how it has to be expressed this way. This is your 10%. The change in R divided by the original R is 10%. 4 times that will be your change in volume or flow of blood. So what we're saying is changing, if we stick with the 10%, now we're ready to consider that. If we change the radius by putting a stint in that expands it 10%, just 10%, we'll increase the blood flow 40%. Pretty good return on your effort. Get 40% more blood flow for a 10% change. So, but the trick here was when they talk about relative change, you've got to focus tight on this. And it could happen to the dV, it could happen to the dr. But it's dV divided by V or dr divided by R that's relative. And then you got to make your decisions based on that when you've got to look for these relative fractions. Yes?
Oh, so why did you, like, what makes you decide on the
Mainly because it said a 10% increase and we never knew what the original radius was. There's no plug-in for the radius. That's why, okay? You want to, well, I didn't realize there was one more example. Would you like to hear a story first?
Yeah.
Here comes a story. Everybody likes stories, I guess. Long ago, I've taught physics since then, but when I first taught physics here, they let me teach that. It was awesome. And we were trying to figure out if we could go someplace and actually calculate the gravity of Earth without just taking it for granted, like the 9.8 meters per second, or the 32 feet per second, which is, is standard. Everybody seems to accept that really, really well. And so I thought it would be really fun if we could go and do some experiments and see if we could come up with that value. So we realized that we would have trouble with air friction and that would cause us to be off by a little bit. So we wanted to go and find out how much air friction affected things, understanding that we knew what the value was and we were going to try to hit it. The tallest place in Rexburg at the time, and it may still be, was the top of the stadium over the college. So we got permission to take stopwatches in my class and all these kinds of spheres. Go over there and have people time them. Because we knew how tall it was. Well, we actually measured that directly too. We took an actual track tape measure. Rather than trying to sight something with an angle and try to figure it with trig, we measured it directly. Took a tape over there, measured it, so we had it right down to the nearest half an inch. And we started dropping things. And we realized air friction would cause a problem. We bought one of those balls at Walmart, big old fat things, and it took forever to come down. We used tennis balls. We used ball bearings. Ball bearings about like that size that come out of big diesel tires or bearings. And we used, I don't know how many different things we dropped. Ping pong balls, that was a dumb one, but we just wanted some extra data. And what we discovered, even with the stuff that was supposed to drop and experience very, very little air friction, that over there at the college, there must be a gravity well. Because we got gravity constant that was way bigger than Earth's gravity constant. And we measured, we took 10 timings on the ball bearings, because we know those would give us the closest one. And averaged those timings. We had different people time it. We did everything, because we did our figuring while we were over there. That can't be. We even had some kids walk across the area where we were dropping the balls and to see if they felt heavier. I could really discover the gravity well. There's no gravity well there. There are gravity wells in certain places. I've never experienced them, but I've heard of the people who have that I trust. But we didn't discover one there, but we could not get our data to come out. And had I done this problem before I did that, I know why. And the main problem was we were using stoplights. We should have been using, can't remember what you call them, photo gates. Do you know what a photo gate is? It's a little thing that sits up like this, and it has a little laser going across like this. And you have one at the top, you have one at the bottom, and you drop the ball through it, or you roll it down an incline or whatever, and it measures. It starts that they're hooked together, and it's a system where as soon as it goes through, it starts the clock, and as soon as it breaks the laser on the other, it stops the clock. Much, much more accurate than this, right? So that was our problem. And that little teeny tiny bit of error in measuring time caused us the reaction time from your eyeballs seeing that you should click, and the electromagnetic impulse to make your thumb click. That's where our error was. It's not very long, but it was enough to cause us to believe something wasn't true. We couldn't figure out our error. So here's the example. Let's see if we can do this. It says you want to calculate the depth of a well from the equation S equals 16t squared. We would actually do negative 16t squared. That's gravity for you. By timing how long it takes a heavy stone you drop to splash into the water below. How sensitive will your calculations be to a 0.1 second error in measuring the time? That 0.1 second could happen because of the impulse going from your ears to your thumb, and it could also happen because it takes a while for sound, a lot longer for sound to come up than light. So you hit your ears before your impulse even goes to click the thing. So you could very easily, especially with a well, an actual well with water in the bottom, you could very easily make a 1 second or a tenth of a second error. How does that affect your estimation of the depth of the well though? The size of ds in the equation is, so we take s equals 16t squared, that's position as a function of time, and we find the change in position, depth, to be 32t dt, dt. And this time they didn't give us a percentage, so we're not doing relative. They actually gave us a 0.1 error in the seconds of change. So we take 32 times, well, let's see, where do we get the 2 from? How sensitive, okay. The size of ds in the equation is 32t dt, depends on how big t is. If t is 2 seconds, the error will be, I said 2, will be 64 times 0.1. You will make a 6.4 foot error if it only takes 2 seconds for the thing to drop before you hear it. quite a bit, the height of a tall man. Okay, and if it's, if you do 5 seconds, if it takes 5 seconds to hear it, then you will have 32 times 5 times 0.1. 32 times 5 is 160. You'll have a 16-foot error in the depth of your well if it takes 5 seconds before you hear something and your timing error is only 1/10 of a second. So can you see why that would cause a problem? We would have been far better to drop it from a far shorter height. We wanted to drop it from someplace really, really, really high so that I was thinking so that our timing errors wouldn't be that bad, wouldn't be that effective. But it turns out if you got a shorter distance to drop it, your error has a smaller impact on your error of measuring this because we went to the tallest place in Rexburg, which is Norway. They wouldn't let us on the buildings, but they would let us up in the stands. Some of the buildings in Florida. So, interesting. If I'd have done this, I would have been able to figure out why we couldn't figure it out. It was horrible. All right, so I am finally finished. Okay? These things right here, they're going to be your bread and butter for this exercise. Make sure you know which one you're using. Okay? All right, good luck with this. I'll give you a few days to work on it.
Good.